Hi and welcome to Trust Me, I'm a Biologist, and today we're going to be talking about the oxygen dissociation curve. So let's get straight into it. The first thing we've got to realize is what hemoglobin actually looks like. Now, hemoglobin is made up of 4 subunits, and they all work together to carry oxygen in this one hemoglobin molecule. Now, the first thing that we have to realize about this is that in its structure where it has got no oxygen attached to it, it's called a T structure, and that stands for tense. So this means it's difficult to get an oxygen attached to it. Oxygen binds onto iron molecules that are in each of the 4 hemoglobin subunits, the chains of hemoglobin. They're alpha and beta chains. It doesn't matter which one's which, it's not particularly important for our level. So what will happen is oxygen will hook on to this iron, and as it does, this molecule becomes progressively more saturated with hemoglobin. So what basically happens is that as a molecule of oxygen attaches to this hemoglobin molecule, it starts to move from its tense structure to its open structure, and you actually see a configurational change of the hemoglobin. In other words, the whole thing starts to open up. And as it starts to open up, it becomes easier to progressively bind more oxygen onto it, which is precisely the reason that this curve looks the way it does. When you're starting to load hemoglobin down the bottom here, it's in its tense structure. And then as you start to add oxygen onto it, in other words, as you become progressively more saturated with oxygen, the curve starts to get steeper, which means a very little change in the partial pressure of oxygen. Partial pressure of oxygen will make a very large change in the saturation of your blood with hemoglobin. We're not talking about one single molecule. We're talking about the overall saturation of your blood. So as you start to progressively bind more oxygen onto more hemoglobin molecules, you get an easier effect of binding oxygen to hemoglobin. When you start to get up here to where the curve starts to flatten out, you're playing a numbers game. Most of the oxygen that's around that's going to be bound to a hemoglobin molecule is already bound to it. So then it's just, like I said, a numbers game about finally binding this last oxygen onto the hemoglobin, which is precisely why you are never, as a human being, more than about 98% saturated with oxygen. Okay? If you ever put a pulse oximeter on your fingers and you see that it's showing you as 100% saturation, you need to start asking questions, because that usually means that it is broken. Okay? Now this works in reverse too. So to get that first oxygen off the hemoglobin is a little bit difficult, and then once the hemoglobin molecule is back in its open structure, unloading of hemoglobin is progressively easier as well until you come down to the last bit. Okay, so how do we actually go about applying this? Well, a way of thinking about the application is that if we are to take our graph and we draw a line here from the 10 kilopascal area up, we can think about this part of the curve as being, let me change the color. We can think about this part of the curve as being this part of the graph here. We can think about this as being a loading region. And then therefore, we can think about this part of the graph as being not a loading region, but an unloading region. Okay, so loading region, unloading region. So I know that I said at the beginning that we probably shouldn't think of this as being about an individual red blood cell with its individual hemoglobin molecules. But the way that I'm going to start to apply this, it's probably easier to think about it like that. So what I'm going to do is I'm just going to clear some of this stuff to give myself some more room to draw, and hopefully I'm going to make you think a little bit about why it is that your teachers and your lecturers start asking you to think about what is going to shift our oxygen dissociation curve left and right. So, we're dealing with red blood cells that are making their way around your circulatory system. They go from your heart to your tissues that are carrying out respiration. Now, this is an important thing to consider. So what happens when we carry out respiration? We're going to consume oxygen. Okay, we are going to consume oxygen. Let's just put this here. We're going to consume. And we're going to produce CO2. So, we always say that when you're drawing an oxygen dissociation curve, you've got your normal curve that kind of goes like this, and then we say to you, what's going to happen if the curve shifts left or right? What does it do to the affinity for oxygen and hemoglobin? And what are the things that make the curve shift right? It's called the Bohr shift. And things that make it shift right are an increase in CO2, an increase in the concentration of protons, which means a decrease in pH, or an increase in temperature. And what are the things that make it shift left? Things that make it shift left are a decrease in all of these things. So that's a decrease in temperature, decrease in CO2, a decrease in concentration of protons, and of course we got the ubiquitous 2,3-DPG to consider as well, but for our purposes I'm just going to talk about these things. So, why is all this important? Well, looking at, I'm going to break my own rules and start talking about a red blood cell. So if we're looking at a capillary bed, so here's your through flow capillary, and of course you've got other capillaries either side of this, but you got your red blood cell, and it's working its way through this capillary bed. What's happening inside this capillary bed? Let's say you're doing a bit of exercise. You're carrying out respiration. You're carrying out gas exchange. In other words, the tissues that are all around here are producing CO2. They're always a little bit anaerobic. That's how you start off work. You don't work immediately aerobically quickly. So they're producing lactate. In other words, they're producing hydrogen ions. And you're carrying out exercise, which means the temperature has gone up. So as the red blood cell is working its way through these capillary beds, it is experiencing all of the things that make your Bohr shift right. And what does this do? If you shift the curve right, you decrease the affinity for oxygen and hemoglobin. In other words, if we were to anthropomorphize things, your hemoglobin molecules want to get rid of the oxygen. They don't want it anymore, so they vomit off the oxygen that they have no appetite for. So in other words, it means that as your red blood cells flow through this environment, everything is set up for it to make it easier for this red blood cell, as it's coming through here, to vent off oxygen, which is precisely what we want. Because why have we got a cardiovascular system? We've got a cardiovascular system because we're too complicated an animal to just carry out things by diffusion alone. So we've got this system that is going to take our red blood cells to the areas that they need to go so that they can carry out diffusion. Don't forget, diffusion is pretty rubbish at moving things over large distances, but it's excellent at moving things over short distances. So this is at the tissues. So at the tissues. So what happens in the lungs? In the lungs, the opposite is true. So if we've got an individual alveolus here, like that, and you've got an alveolar capillary coming around it like this, and the red blood cell this time is coming through here, and it's working its way around here, and out there like that. But what's happening inside the alveolus? We're breathing in room air. The concentration of CO2 in room air is 0.03%. Decreased CO2. What temperature is the air? It's 21 degrees. As it warms up, as it comes inside you, it's still nowhere near 37 degrees. Decreased temperature. So we're setting up everything in here that is going to shift your bore curve left. In other words, what we're doing is making it so that the red blood cells want to hold on to oxygen. In other words, we're making the loading easier. So O2 goes in. So actually, what we should probably be doing is thinking about this curve in a very different way. And it's something that I've been encouraging my students to do recently, is to think about it like more like this. Let me just cut this out a second. I'll fill this back in. Is to actually redraw the curve. So we've got our axes like this. And we've still got percent saturation, and we've still got PO2 over here. We're never more than about 75% desaturated, and we're never more than about 98% saturated. So actually, we probably shouldn't think about this average curve that we always do, and we should actually draw it like this, and say that it's more, looks a little bit more like a hysteresis curve. And that actually this area coming down here is what we experience when we're trying to unload, and this area coming up here, this curve here, is what we experience when we're loading. So what you've actually got, or what I should say is what you've never got, is this single oxygen dissociation curve. Indeed, what you've always got is a situation where the curve is constantly oscillating from right to left, depending on whether you're in the tissues or in the lungs. So why not just skip the middleman completely and think of it like this? You've got a curve that you experience when you're unloading oxygen, and this is what you find in the tissues. And a curve that you experience where you're loading oxygen in the lungs. I hope you found that useful. As always, subscribe to the channel, like, comment, tell your friends, and we can do more physiology together. And if there's anything that you want me to go over, please drop me a message.